Guys, once again, you need to be grabbing the lab that's due. That's the sheet of paper in your graph. But then also grab some note-taking materials. And as you're doing that, guys, I want to tell you about Friday. Friday, we're going to take the test over this unit. And guys, here's the scoop on this test. On this test, if I were to take your scores on this test and graph them, we would actually get an inverted bell-shaped curve. Historically, on this test, you're going to get an A or you're going to get an F. And for those of you that get an F, for many of you, it's going to be the worst test score you've ever seen ever in your academic career. So guys, what's going to separate the A's from the F's? And guys, frankly, the answer is, did you study? And I know that sounds cliche, but guys, this test, more than any other test you're going to take in this class this year, you're not going to be able to fake this. The details are so fine and so important that if you're not reminding yourself that the relationship between polarity and intermolecular force is direct, but then the relationship between intermolecular force and volatility is indirect, but with boiling point it's direct, but with cohesive force it's direct. Because if you're not reminding yourselves of those things, this is going to back up on you in ways that you've never seen before. So guys, study for this test. You know how to do that. Print the study guide. We've talked about study strategies, the no's and the do's. Study for this test. Guys, with that said, I will not be here on Friday. Frankly, I don't know if you care to know, I'm just not going to come to school. My daughter is now 13 years old. Her birthday was a week ago, and she's decided she's not a little girl anymore. And so her room that used to be pink and rainbows and unicorns, well, when you're 13, that's not cool. And when you're 6, that's great. But 13, not so. What she wanted for her 13th birthday was to redecorate her room. So over Christmas break, we repainted. But the thing that she asked me for was a window seat in her room. Her bedroom has a little alcove with a window in it. And she asked if I would build her a window seat. And I've been working on this thing for a week, and I just can't get it done because when I'm at home, my boy's like, hey dad, let's go do this, or my daughter wants to do this, or my wife wants me to do something. And I just finally said, I need a day with nobody in my house so I can get this done. So frankly, what I'm going to do is I'm going to lie to my daughter and tell her that I'm going to give her a ride to school. And I'm going to give her a ride to school, drop her off, and instead of go to work, I'm going to turn right around and go back home and finish her bench so that when she comes home from school, it's done. So, yeah, I know, right? Dad points. So, guys, I'm not going to be here. So that means you're going to take the test without me. No big deal. But I just need to tell you how this is going to go. So, guys, when you come in on Friday, there's either going to be 1 or 2 adults, well, older than you, people in the room. One of those people may be Mrs. Clay. You know that increasingly throughout the semester, she's going to be working with you all. But guys, and this is just nuts to me. Whether Mrs. Clay is here or not, I have to get a sub. Understand this makes no sense instructionally. This is a legal issue because while Mrs. Clay in 7 weeks is going to be a fully qualified teacher, she doesn't have district insurance. So if one of you keels over and dies, she's not insured, but a substitute is. So whether she's here or not, I've got to get a sub. So here's how this is going to go. If Mrs. Clay is here, she's in charge. She should be in charge. She knows what she's doing. If Mrs. Clay, and then if that's the case, there will be a sub, and we'll just tell her to stay out of the way, or he. But guys, if she's not here, then the sub's in charge. But regardless, here's how the day is going to go. You're going to take the test. Then when you're done with the test, you're going to turn it in. And this is weird. Hear me out. You're going to turn in the test, and then you're going to get another test. Here's what's happening. Guys, BYU, which is where Mrs. Clay goes to school, requires that for a unit that she teaches, she does a pre-test and a post-test in the minds of people that aren't teachers but pretend like they know how to teach. We call them university professors. Guys, in the mind of these university professors, the way to gauge the ability of a teacher is to test their students on the material without having taught any of it, then test them after, and their improvement in scores is the learning that happened as the result of teaching. We're going to pretend that's true. So, guys, what that means is Mrs. Clay has got to do a pre-test with you. Here's the problem. You're going to take this test home and you're going to be like, I have no idea what any of this means. Guys, you're not supposed to. You haven't seen any of this stuff before. So when you take this test home, here's what I'd like you to do. The best you can, fill out the bubble sheet. Guess when you need to, which will be most of the time. And then there will be a handwritten page. I would be really surprised if any of you know anything on the handwritten page. So at least read through it, and if there's any of these you happen to know, please write them down. But understand, you're not going to be graded upon the quality of what you did. I just want you to look at it. You know what I'm saying? So then, guys, you'll turn that in on Tuesday. You'll get credit for trying it, not for doing it right. You guys good? Okay, so that's everything I wanted to talk with you about. Guys, grab your notes page and let's get started. You're thinking, wait a minute, weren't we going to turn in the labs? In a minute. So guys, here's what I need you to do. Did we already title our notes? Not yet? Okay. So guys, the date today is the 17th. The topic for your notes today is solutions and colligative properties. So guys, as you're doing that, you may remember when we started this unit, right when we got back from Christmas break, we started the unit by asking some questions. And some of those questions you might have found compelling. Like, for example, why does sugar not dissolve in gasoline? And initially that sounded weird until you realized that's an eco-terrorism issue. And then maybe, guys, the question that we ask along the way where we said, why do we put salt on our roads in Utah? Although not this year because it's not really winter. But guys, why do we put salt on the roads in Utah in the winter? And I think most of you know the answer. Makes the ice go away. But then, guys, we ask the interesting follow-up question, which is, why do they not salt the roads in Wyoming? Well, guys, when I ask you those questions, there was actually another question that I wanted to ask you, but I couldn't because it would have given away a lot of what you did 2 times ago in lab. But we can ask it now. Don't write it down, but guys, why? When we did the lab, when you guys walked into this class months ago, even days ago, you thought water boiled at 100 degrees Celsius. You've been taught that. Water boils at 100 degrees Celsius. But then you found out it didn't. Because the question is why? Why does water not boil at 100 here in Utah? Well, guys, we're going to talk about that. But along the way, we're going to answer this interesting question as well. Is there anything that we can do to make water boil at 100 degrees Celsius here in Utah? And guys, to answer the question, what I'd like you to do is this. Grab your labs that you're about to turn in and look at your graph. You got your graphs? Now let's ask the question again. Looking at your graphs, is there anything we can do to make water boil at 100 degrees Celsius in Utah? And what would your graph tell you? Yes, add salt. Guys, did all of your graphs have a positive slope from lower left, upper right? What is that telling you? Well, it's telling you x-axis, as you add salt, y-axis, the boiling point goes up. And if you added enough salt, eventually you could get the water to boil at 100 degrees Celsius. Now, guys, the interesting follow-up question is why? Why does adding salt to water make the boiling point go up? Well, guys, guess what? You've already answered that question. Where? In the conclusions. Go read your answer. Guys, the conclusion question on the lab said, keeping in mind, paraphrasing, keeping in mind intermolecular forces, why does adding salt do what it does to the boiling point of water. Now, guys, you took your best guess at this. And Ellie, you came and asked me earlier, are you going to be grading this or something like that? And guys, the answer is yes, but no. I am going to read your answers to the conclusion question. I just want to know what you were thinking. I'm not going to expect you to get it right. Why not? Novel idea. We haven't learned this yet. But guess what we're going to do today? We're going to learn this. Guys, the very last thing we're going to talk about today is why did the boiling point of the water go up when we added salt? We're going to answer the conclusion question today. What I want you to do right now is read your answer. Did you all get a chance to do that? Okay, turn in your labs, and then we're going to come back and answer the question. So guys, staple your graphs to the back of your cover sheets. Put them in the basket. You guys remember how to staple, right? What did we decide? Diagonal? Diagonal staples seem to be best. We're going to be okay. Did you do the lab makeup? So last time in class we did a lab. Have you ever done a lab makeup before? Okay, so the lab makeups are actually take-home things. You don't have to come to class to do it. You just get on our website, and today's Wednesday, last Friday. Just go to Friday, and it'll say Colligative Properties Lab, and then there's a makeup. Click on that link, print what's there, and then just do it. When you do, don't put it in the basket, give it to me. Okay? Hey. That's a great question. And so the quick and dirty answer is no. The real answer is yes. So polarity is based upon two things: the difference in electronegativities of the bonds, but then also the shape of the molecule, right? And we understand that when we heat molecules up, the molecules vibrate faster, right? So do the bonds. These bonds will actually start to vibrate as well, and as they do, that can affect the polarity. Not as much, slightly, but the technical answer is yeah, it does. Yes, but the difference there isn't a polarity issue. It's that the water molecules in hot water are actually moving faster, and they collide more frequently with the dirt and therefore carry it away more quickly. Yeah, yeah. You guys all done? What do I do next? Gather up your labs. Wait, no. There you go. Yeah, you almost threw down the wrong staple. I know, right? There we go. All right, so guys, what we're going to do now is we're going to spend the remainder of the day and we're going to answer these questions. But to do so, we need to actually pick at these questions one at a time, and this then is where you want to start taking notes. So guys, question number 1, why does water boil at 96 rather than 100? Well, guys, what we're going to do is to answer the question, we're actually going to ask a more general question. So if we want to know why water boils here at 96 rather than 100, what we really need to understand is the answer to this question. What determines the temperature at which water boils at in the first place? Because if we know the answer to the second question, we can then apply it to the first question and figure out the answer. So guys, the question that we're actually going to talk about now is what factors determine the temperature at which water boils? Now guys, here's the thing. You already know part of the answer. Or maybe, yeah, if you don't know this answer, you're not ready for the test. So guys, we're going to let this be our sample of water. As soon as you're done writing, we're going to review the little bit that we've already talked, well, the lot of bit that we've already talked about, and then we're going to get to the whole answer. So guys, here we go. Water. How do we describe what is going on in liquid water? What's our mental picture? Mosh pit. It's full on violent crazy in there, right? What happens to the water as we heat it up? It mosh pits even faster. And these things get moving faster and faster and faster. And finally, they have enough energy that what breaks? The intermolecular forces, and the molecules leave, and we call that boiling. So guys, one of the factors that influences the boiling point of water is the strength of the intermolecular forces. But guys, here's the problem. If that was the only thing that affected the boiling point of water, then water would boil at the same temperature even here in Utah. So why does water not boil at 100 degrees here in Utah, Zach? It's because of altitude, but please don't write down altitude. Because guys, altitude is actually a function of a bigger idea, which is atmospheric pressure. So guys, weird thought coming. You ready? When you go outside today at lunch, and when you gaze up into the sky, actually don't, because the inversion's setting in and you might choke and die. But guys, assuming that there is not an inversion, when you look up into our bright blue skies, what are you looking at? And guys, the answer is miles and miles of atmosphere. And so guys, when you look up, you are literally staring through multiple miles of air. And if you can't picture what I'm talking about, literally it looks like this. When you, and you don't even have to be looking up. If you're just standing there, there is a column of air sitting on your head that goes up miles and miles and miles. And guys, air is made of matter, and matter has mass, and gravity pulls on that mass and gives it weight. Remember when we talked about that? So guys, the question then becomes this: how much does the air weigh that is sitting on your face when you look up? Well guys, this is weird and somewhat disturbing. How big is this piece of paper? 8.5 by 11. So what is the surface area of this paper? 8.5 times 11 square inches. You know what I'm saying? Here's the thing that's weird. It is approximately the surface area of your face. A piece of paper actually has approximately, like from here forward, if you could like skin yourself, if you could take, that's weird, that sounds funny with my microphone. If you could take the skin off of your face and lay it flat, it would have approximately the same area as a sheet of paper. So now we can picture our sheet of paper. I know, right? And so guys, sitting on this sheet of paper, there's air. And that column of air goes up miles and miles and miles. And how much does it weigh? Guys, this is a sobering answer. 1,350 pounds. So guys, there's 1,350 pounds of air pushing down on this paper. And you know from experience, there's no way I can lift 1,350 pounds. So why is it not, and the paper pushing down? Like why am I not being asked to support 1,350 pounds of air? Exactly. It also pushes up. So guys, in addition to pushing down, it pushes up, and it pushes from all directions. And as a result, I'm not supporting 1,350 pounds because it pushes in all directions. So guys, what about this? Why is your face not being smushed by 1,350 pounds of air? Because you leak, right? Guys, there are holes in you. Your ears, your nose, your eyes. You know your eyes leak? You got those little ducts? Guys, your mouth, your body leaks. And so the air not only pushes in, it goes in and pushes out. And as a result, the in and the out are equal, and you don't get smushed until you drive to the top of Squaw Peak. And then what happens? Your ears pop. Guys, why do your ears hurt when you drive to the top of Squaw Peak?
Because the pressure inside your body outweighs the pressure on the outside.
So let's talk about why. So guys, right now, standing here in Utah, you've been here long enough that the pressure in and the pressure out is equal, right? Now, when you drive to the top of Squaw Peak, you're going up in the atmosphere. Does that make sense? You're going up in elevation. And so, guys, as we go up in elevation, there's now less of our atmosphere above us. So if we're down here at sea level, there's all this atmosphere above us. If we come up here to Utah, there's less atmosphere above us. If we go up here to Squaw Peak, there's less atmosphere above us, and less atmosphere means less weight, means less push. Now, guys, this is no big deal relative to your nose and relative to your mouth. Although if you have a sinus infection, have you ever had that experience of going up in the mountains with a sinus infection and you feel like your head's going to explode? Guys, why does that happen? And here's the reason. Think about your ears. So there's pressure inside and outside your ears. But how does the air get in and out of your ears if you've got eardrums? And the answer is there are these little tubes called the station tubes. And it actually drains your ears down anyway. So the air can get in and out, but it doesn't get in and out very well. So as you go up in the atmosphere, the pressure on the outside of your ears goes down. So there's less pressure in, but there's still high pressure out, and it makes your eardrums bulge, and that hurts. And so eventually, so what do you do when your ears need to pop? Well, you start to yawn, and you chew gum, and all these other things that are supposed to help. But why does that help? Well, what it does is it actually stretches your eustachian tubes, and eventually you can get them to open up, and the air goes poop, and it equilibrates, and that feels like it pops. But what's actually happening is the extra air pressure inside your ears finally leaks out. It feels like a pop. Now the pressures are equal, and it doesn't hurt anymore. You guys, of course, knew all of this stuff, right? What do they teach you in this school? Go ahead. Yeah. Mm-hmm. Yeah, same thing, but the opposite. And you don't even have to be a scuba diver. If you've ever dove to the bottom of the diving tank at the Orem Rec Pool, so you get down there and you're 10 feet down, right, in the water, and there's a lot of pressure down there. And so now you've got water pushing into your ears, and then you've got the air trying to push back out, and that water puts so much more pressure. So what do they teach you to do? And if you're a diver, you know this. What do? You pinch your nose and blow. And why do you do that? Well, you go, okay, that's weird. You can actually try it, and you can feel it. You can actually feel your eardrums bulge out. If you hold your nose and blow, I can even hear my eardrum, because now what you're doing is you're pushing out against the water pushing in. Now my ears need to pop. But it's the same thing in reverse. So if the pressure is higher on the outside, you need to blow out to make it equal. If the pressure is lower on the inside, then you need to let that extra, or lower on the outside, you got to let the extra pressure out. Does that make sense? Do you get the idea? Mm-hmm. No, because the pressure can't get out because it's water. And so you just need to create an artificial increase in pressure on the inside to offset the water pressure on the outside. Does that make sense? Yeah.
So have you had some kind of rains or kind of few days before? Does that have something to do with it?
It just means someday you're going to be a phenomenal poet. I have no... If I said yes, would you believe me? Yes. No, I mean, okay, so seriously, there could, okay, so there could be some of that, but let's talk seriously about the science. So you guys have heard of high and low pressure, right? So when the weather is bright and sunny, that's high pressure. When the weather is cloudy and gloomy, that comes with low pressure. And literally, we're talking about the pressure of our atmosphere. So if it's a cold, gloomy day, the pressure outside drops. And so there may be something about your body that when the pressure drops, it could create an imbalance in pressure in your ears or something like that, and it could cause headaches.
It also gets worse when it's warm.
Yes. Yeah, it could just be motion sickness.
Well, I have motion sickness, but it's completely different. It's like when I get in my car, the headache that I have outside because the pressure is 10 times.
Sounds to me like you just need a better doctor. I have no idea. I don't know. I could make up stuff, but I'd just be making up stuff. So, yeah. Okay, so guys, you get this idea with elevation and pressure? Y'all good? Okay, so let's then talk about what this has to do with boiling. So let's go here. So now, guys, looking at a beaker full of water, we can now bring this idea, no pun intended, to bear on water. So guys, the idea now is this. In order for this water to boil, you already understand the idea that the IMFs have got to break, right? But now, given our previous conversation, what else could you imagine keeps this water from boiling? Air pressure. Guys, the same 1,350 pounds of atmospheric pressure that's pushing on this paper also pushes on the surface of the water in the beaker. So certainly it's not 1,350 pounds, right? Because this isn't as big as a piece of paper. So I did the math, and it's actually, oops, drawing dots. Guys, it's actually 88 pounds. So on the surface of a 250 milliliter beaker, there's actually 88 pounds of force pushing down on the surface of this water. So not only do the IMFs have to break to get the water to boil, it also has to push up with more force than the atmosphere is pushing down. So guys, when we take this water from sea level up to Orem, why does the water boil at a lower temperature? There's less air sitting on the water. Because there's less air sitting on the water, there's less atmospheric pressure. It's easier for the water to jump out, and the boiling point goes down. What's that? Beautiful. So where does the salt come in? And the answer is it's completely unrelated to what we're talking about. But what we've now done is we've got our eyes, Ethan, around both ideas. So what determines where water boils? Some of it has to do with altitude and atmospheric pressure. Some of it has to do with what the salt is doing. And what we're about to do is talk about both of those. And we're going to bring them together in just a minute. Go ahead. So, no, it's actually not. Well, you'll see. But I want you to come back to that idea in just a minute, because I think I know where your head's going, but we're not quite ready to get there yet. So guys, are you settled on this idea of why water doesn't boil at 96 here in Orem? Is that okay? So guys, let's then bring that together and make a statement out of it. So guys, it goes like this. So, just blanket statement. What does atmospheric pressure have to do with the boiling point of liquids? Well, guys, higher altitude, like Orem, 4,600 feet above sea level. Higher altitude results in lower atmospheric pressure. Lower atmospheric pressure means it's easier for the water to jump out of the beaker. The boiling point goes down. And I know some of you right now are wanting to run ahead and bring into this the conversation about salt, and we're going to do that. But right now, guys, we just got to make sure that you're comfortable with this idea that says the other thing that influences boiling point is atmospheric pressure. The lower the atmospheric pressure, the lower the boiling point. Are you guys comfortable with that idea? Is that okay? Anything else there you want to explore? You guys okay? Okay, so guys, with that then said, let's now go where you guys want to go, which is to talk about intermolecular forces. And this is where we started the day, right? We shared this idea that we already knew that in order for the water to boil, the intermolecular forces have got to break. So this isn't new, but let's at least review to make sure that we're clear. So guys, the fundamental relationship is this. The stronger the intermolecular forces, the higher the boiling point. And you may remember we talked about it relative to alcohol. And we said this, alcohol is a less polar molecule. As a result, its intermolecular forces are weaker. It boils at a lower temperature. Water is a more polar molecule. Its intermolecular forces are stronger, and it boils at a higher temperature. So guys, if you remember this idea, that's all that this is saying. Water has got stronger IMFs, higher boiling point. Ethanol, lower IMFs, lower boiling point. So guys, now what we've done is we've got our arms around both answers. So what are the things that determine the temperature that a liquid boils at? Atmospheric pressure and intermolecular force strength. You guys comfortable with that? Okay. And then now let's answer the first question. Coming back here. So guys, exactly the same place we started. So what can we do? If we now understand the factors that determine the temperature at which water boils, what can we do to make it boil at 100 here in Utah? Well, guys, we're going to do this in order. So we understand that atmospheric pressure and intermolecular force strength are the factors that determine boiling point. So if we want to make the boiling point go up to 100, these are the things that we need to mess around with. So let's do them one at a time. So as we've stated before, to make the boiling point go up, we need the atmospheric pressure to go up. For the same reason that if we go to a higher altitude, the pressure goes down and the boiling point goes down, like here in Utah. Guys, if we want to make the boiling point go up, we've got to increase the atmospheric pressure. Doesn't that make sense? Higher atmospheric pressure, more force down on the water, harder to boil, the boiling point goes up. Guys, the question is how? What could we do to this water to increase the atmospheric pressure on it and therefore increase the boiling point? Say it, I heard it, yeah, go say it again. Guys, take it to sea level. Let's rent a bus and go to San Diego. I was about to say something derogatory about that's exactly what the fine arts department would do. Understand, I'm coming from a point of jealousy because you guys travel better than any department in the school, and I love it. But could we do that? And then we could go to Disneyland. Yes. I know, right? For science, of course. All right, never mind. All right. So, guys, yeah, that's one of the things, just a second, Ethan. That is one of the things we could do. We could take this beaker of water and we could go to San Diego. Why San Diego? What's the elevation in San Diego? It's sea level. And so, guys, what temperature does water boil at in San Diego at sea level? 100 degrees Celsius. That's where that number 100 degrees Celsius came from. That's the boiling point at sea level. So if we took our water down to San Diego, now it boils at 100. The problem is this really doesn't answer our question, because the question is, what can we do to get water to boil at 100 in Orem? And if we take it to San Diego, it's not in Orem anymore. But it would work. Go ahead. Yeah, so what about that? Have you ever seen those pictures? Guys, Death Valley, this is cool. So Death Valley, you know, is below sea level, right? If you've ever been there, or look up these pictures. So Miramar, are you guys familiar with Miramar? It's a Navy base. They fly their F-16s out of Miramar. And guys, these jet pilots will actually fly their F-16s through Death Valley, and there's a line on the wall that says 0 degrees. It's actually a line that's at sea level, but it's multiple hundreds of feet up the side of and they fly their jets through there right at the line to make sure their altimeters say 0. Pretty cool. So, at least that's cool to me. So, but guys, you guys don't care. That makes me sad. But, and some of you guys are going, really? Yeah, I've seen pictures. So what about that? What if we took that beaker of water and went to the bottom? So now we're lower than sea level, right? So what's the pressure going to be all the way down in the pit of Death Valley? The pressure is going to be even higher, so what will happen to the boiling point? It's going to be even higher. It's probably 101 or 102 degrees. So the lower we go, the higher the boiling point goes. Yeah, go ahead. Yeah. Absolutely. Yeah. And you know the thing that's crazy about that? So back in the day when I was single, I used to climb tall mountains. And even 14,000 feet, if any of you have been above 14,000 feet and camped up there, it's crazy because you're camping even at 14,000 feet and it takes forever to cook spaghetti. Because even at 14,000 feet, the boiling point has gone down low enough that the water doesn't get hot enough to cook things like spaghetti very effectively. Imagine the guys on Everest. These guys that climb, it's crazy. The boiling point high up Mount Everest is actually low enough that you can almost stick your hand in boiling water and not get scalded. That's the question. So guys, and that's actually leads directly into what we're about to talk about. So guys, we understand that we could take this water down to sea level, or as Ethan was saying, even down into the pits of Death Valley, and we could make the boiling point go up. But what if we wanted to make the boiling point go up, but stay here in Utah? And you're right on it. You said put a lid, right? Put a lid on the container. So guys, why would that make the boiling point go up? Well, the thing is, just a second, Zach, you all are familiar with this because that's what this is. What is that? It's a pressure cooker. And guys, how does it work? Well, the answer is this. You put water in a pressure cooker, and then just like you said, you put a lid on it, right? And when the water boils, the steam goes up here. But if there's a lid on it, where does the steam go? It's trapped. And as we get more and more steam up here, that creates greater and greater pressure. And that pressure not only pushes out, it also pushes down on the water that it came from. And as the pressure in there increases, it makes the water harder and harder to boil. You know what? Let's not take this because this thing weighs like 2,000 pounds. Hey, so of it because it seriously weighs like 70 pounds. Yeah, no, let me do it. No, just let me do it. Yeah, thank you. So guys, the idea here is that as we increase pressure in that pressure cooker, we're literally creating an artificial atmosphere that has higher pressure. And as the pressure goes up, the boiling point goes up, and that allows the water to get even hotter. So that's what the mountain climbers on Everest do, is they carry pressure cookers with them and they tighten that lid, and that allows the boiling point of their water to go up. That's exactly what they do. Yeah. Oh yeah, but really the water boils really fast, right? Because the water doesn't have to heat that hot to boil, but then it takes forever to cook your food because the water's not that hot. And you even saw that probably up in the Uintas or wherever you were. So yeah. So guys, that's why pressure cookers work, because they do this. They create an increase in atmospheric pressure simply by creating an artificial atmosphere. Does that make sense? You guys good? Okay. So guys, we are halfway done with the concept. We now understand what we could do to make the boiling point go up relative to atmosphere. We can either increase atmospheric pressure by decreasing elevation, or we can increase atmospheric pressure by using something like a pressure cooker. But guys, that's only half the story. What is the other thing we can do to make the boiling point go up? And this is where Ethan wants to go, and this is where Justin wants to go. Guys, the other thing that we can do to make the boiling point go up, and you learned this in the lab, add salt, right? But guys, why does that work? Well, guys, the reason it works, and this is what you need to jot down in your notes, is because it strengthens the intermolecular forces. So guys, how do we strengthen intermolecular forces? Add salt. So why does this work? Well, we'll talk in a second. But before we do, we need to remind ourselves of two terms. Do you guys remember back in early September when we talked about that triangle and we talked about homo and heterogeneous and elements and compounds and solutions and all of that stuff? Guys, on that day, you learned these two terms. You learned that in order to create a solution, you need a solute. That is the thing that is being dissolved, the salt. And then we need a solvent. That is the thing that's doing the dissolving, the water. And guys, a solution contains both a solute and a solvent. Go ahead. It doesn't, and we'll look at that in a minute. So guys, the question then becomes, why does this work? Why does creating a solution, adding salt to water, strengthen the intermolecular forces and therefore make the boiling point go up? We already know this works. You saw that in lab. Put salt in water, the boiling point goes up. Why does that happen? Because the intermolecular forces are getting stronger. Why? And guys, in order to understand why, we need to talk about what happens when salt dissolves in water. So this is the way we're going to unravel the rest of the day. We now know the answer to the question. What could we do to make the boiling point go up? 1, increase atmospheric pressure. How do you do that? Take it to sea level or put it in a pressure cooker. What's the other thing you can do to make the boiling point go up? Add salt. You learned that in the lab. So when we add salt, that makes a solution. When we make a solution, the intermolecular forces get stronger. They're harder to break. The boiling point goes up. But why? And to understand why, we're going to talk about how do solutions form. Once you understand how solutions form, you'll be able to bring all these ideas together. We're going to talk also then about how this affects freezing, and then we're going to call it a day. Are we ready to move on? Is that okay? You guys all caught up? Okay. So guys, in order to understand this, what we need to do is we need to talk about how do solutions form. This is a question of solubility, and you want to scratch that term in your notes. So guys, solubility simply speaks to, will something dissolve in water? So guys, that then becomes the question. What determines if something will dissolve in water? Why does salt dissolve in water and oil doesn't? Well guys, the answer is simply this. Why do some things dissolve in water and others don't? It's all a question of polarity. So in order for something, a substance, a solute, to dissolve in water, the polar water molecules have got to be strongly attracted to whatever it is that you're trying to dissolve. So guys, why does salt dissolve in water? Because polar water molecules are attracted to it. Why does sugar dissolve in water? Because the polar water molecules are attracted to it. Why does oil not dissolve in water? Because the water is not attracted to it. Why not? Because the oil is not polar. So guys, if you ever, not that you would ever want to do this, but if you ever need to test a substance to see whether or not its molecules are polar, throw it in water. If it dissolves, it's polar. If it doesn't, it's not. It's really that simple. So we're going to actually sort of define that idea. So what does this mean? Well, it means if a substance dissolves in water, it's got to be polar, like salt, sugar, Kool-Aid drink mix. Anything that you know that dissolves in water is polar. So what about the stuff that doesn't dissolve in water? Well, it's not polar. It's really that simple. But guys, in order for this to really make sense, well, I know that you're writing down the words and you feel like, okay, I get the words, maybe. This really comes home when you see the pictures and the videos. So what I want to do to help you better understand this is first I'm going to show you an animation. And guys, animations are like cartoons. They're artistic renderings of what this might look like. But then after that, I actually want to show you the simulations, the representations that supercomputers have generated by actually looking at what this really looks like. So you may remember I showed you the simulations of what solids, liquids, gases, freezing, and boiling look like. Well, I'm going to show you simulations of what dissolving looks like as well. You guys all caught up? Yeah.
Is there any kind of reverse concept where you could reduce the boiling point?
No, no. So you can't reduce the boiling point by doing that. What you can, well, it's sort of not the answer, but you can sort of reduce the boiling point by adding something to it that boils at a lower temperature. So for example, if you were to put alcohol and water together, playing bartender, whatever it is that you made would actually boil at a lower temperature because the alcohol would boil off more easily. But no, there's nothing that you, well, this would be a great, I don't know if this would work. Would soap make the boiling point of water go down? So this is way tangent, but we can talk about it. Soaps contain, many times, soaps contain substances called surfactants. And as the name sort of implies, a surfactant is a substance that breaks the surface tension of the water. And that's helpful because if you can break the surface tension of the water, then the water can get into the clothing and grab a hold of the dirt. So a lot of times, soaps actually contain what are called surfactants. And they do that by weakening the intermolecular forces in the water. And so technically, if you could add a surfactant, soap with a surfactant in it to water, it might drop the boiling point. That would, or do any of you guys work on your own cars? Do any of you do that? Because there's a substance that's actually, it's weird, it's called water wetter. I don't know if you've ever heard of it, but it actually, you put it in your radiator, and it actually decreases the surface tension of water so that the water can attract to the radiator and transfer heat more easily, and that's actually pure surfactant. That would be a great science fair project. Let's not do a science fair project. Go ahead. That's all right. Yeah. Mm-hmm. Yeah. Yeah, right. No, so, and we'll talk about it briefly, guys. This is, don't worry if this doesn't make sense. So the triple point is actually this weird set of conditions where the temperature and pressure are just right so that the solid, the liquid, and the gas phase all exist at the same time. For water, the triple point is just a fraction of a degree above 0 Celsius. But the pressure is like almost a total vacuum. So every substance has this magic combination of temperature and pressure conditions where all three phases exist at the same time. So it does have to do with pressure, but also temperature. And we talk all about that in AP. Okay, so guys, here's where we're at. We're now ready to finally wrap all of this up. So here's what we know. Can we change the boiling point of water? Yeah, one of the things we can do is increase the pressure. How do we do that? Well, we either go to the ocean or we put it in a pressure cooker. What's the other thing we can do to make the boiling point go up? Strengthen the intermolecular forces. How do we do that? We add salt. Why does salt make the intermolecular forces stronger? Well, guys, to answer that, you need to understand what happens when salt dissolves. So, animation first, simulation second. So guys, this is what it looks like when salt dissolves in water. So can you see the similarities? Look at what I've got. So this is how we represent salt. The greens are the chlorides, the sodiums are the grays. So it's just really a representation of this. But then guys, we're gonna bring in the water. Here comes the mosh pit. And guys, these water molecules slam into the ions of the salt, and they carry the salt ions away like little tugboats carrying ships away into the harbor. They literally latch onto these ions and drag them away. Now guys, if you're paying close attention, you may have noticed this. The molecules of water do not orient themselves the same around the sodiums and the chlorides. Why not? Well, guys, drawing in the polarity arrows for water, we know that oxygen is more electronegative than hydrogen, so the polarity of the water molecules, they're not symmetrical, so they're polar. The polarity of the water molecules goes like this. So the positive end of the dipole is attracted to the negative chloride ions. And then, guys, similarly over here, the negative ends of these dipoles are attracted to the positive sodiums. So guys, when these water molecules surround the ions, they do it so the positive dipoles are attracted to the negative ions, and the negative dipoles are attracted to the positive ions. Does that make sense? But guys, the question then becomes this. What are those forces of attraction? What's going on in here? What are these forces that stick the water to the ions? Intermolecular forces. So guys, this then becomes the idea. Imagine, and some of you are getting it already, guys, imagine that this is a beaker of water. And if we want to boil this beaker of water, now that there's salt in it, this water isn't just attracted to other water, this water is now attracted to the salt ions. And what do you know about the strength of these attractions? Is it weak or strong? Strong. How do we know that it's strong? Because if it wasn't, the salt wouldn't dissolve. So guys, the logic goes like this. Does salt dissolve in water? Yes. Why does salt dissolve in water? Because the attractions are strong. And guys, these strong attractions are harder to break. So if this water molecule wants to jump out and boil, it's harder for that water molecule to jump out because it's strongly attracted to the salt, and as a result, you've got to heat it up hotter to make it boil. Go ahead. That's exactly what that means. And guys, that's where we're going. And actually, the thing that's weird, that lab that you did last time, we used to do it with sugar as well. We would have you do the whole lab with salt and then come back and do the whole lab again with sugar. It just made everything really sticky, so we stopped it. But guys, imagine this. Imagine if we then went to do this lab again with sugar, and so those little vials were full of sugar instead of salt. Guess what your graphs would look like? Exactly the same. Not just upward. So long as you're adding the same amount of sugar as salt, the graphs would look exactly the same. Because guys, it doesn't matter what you're dissolving in the water. If it dissolves, the forces are stronger and the boiling point will go up. And that's actually what I want to show you next. So guys, it looks like this. So we understand now the boiling point goes up because those attractions are stronger. But guys, we can actually see that this carries itself down to things like sugar water as well. So here we've got a beaker of water. We've got all these forces of attraction to get the water to boil. The forces have got to break. Well, now we've got salt water. And all of these molecules are attracted to the salt ions. What do you know about those forces of attraction? They're really strong. And because they're strong, they're hard to break, and therefore the boiling point goes up. Well, guys, what about sugar? Does sugar dissolve in water? Why does sugar dissolve in water? Because the forces are strong. And guys, those attractive forces between the sugar molecule and the water molecules, those forces are stronger, therefore they're harder to break, therefore the boiling point also goes up. And guys, it does not matter what you dissolve in the water. It could be sugar, it could be Kool-Aid, it could be salt. It does not matter. If it dissolves in water, the boiling point will go up. And interestingly, the boiling point will go up the same amount no matter what you dissolve, so long as it's the same amount. So if you put equal amounts of salt in one beaker and sugar in the other, their boiling points will go up the same. Did that answer your question? Isn't that weird? But that's how it works. So guys, are you okay with this idea about why boiling point goes up? Okay, then let's wrap this up. Guys, the thing that Justin mentioned is actually an example of something that we need to talk about to wrap up this day. So scratch this in your notes. Guys, these are what are called colligative properties. So what is a colligative property? Well, guys, a colligative property is a property of a solution that is only determined by how much stuff you're dissolving. It could be sugar, it could be salt, it could be lawn fertilizer, it don't matter. If it dissolves in the water, the boiling point will go up, and the more you add, the more it goes up, and it doesn't matter what it is. Now, guys, understand that this is true not just for boiling. And there's one other we're going to talk about. But fundamentally, the idea with these colligative properties is it dissolves in water and it makes stronger intermolecular forces that change the way the water behaves. And it doesn't matter what you're dissolving, as Justin said. It doesn't matter what you're dissolving. It only matters how much you're dissolving. So guys, we already know this. When we dissolve salt in water, the boiling point elevates. The boiling point goes up. So guys, scratch this down with me. This is called the boiling point elevation colligative property. So why does this happen? Why does adding salt to water make the boiling point go up? And that was your conclusion question, right? So regardless of what you wrote, guys, this is actually the answer. And you already know this. Why does adding salt to water make the boiling point go up? Well, guys, it goes like this. If the solute dissolves, the intermolecular forces are stronger in the solution. How do we know that's got to be true? Because if the forces aren't stronger, it wouldn't dissolve. So, guys, if it dissolves, the forces are stronger. Therefore, the forces are harder to break. Therefore, the boiling point goes up. Guys, that's the logic behind it. Salt dissolves in water. Why? Strong attraction. Those strong attractions are more difficult to break. As a result, the boiling point goes up. Did any of you get that in your conclusion answer? Did you? Nice job. Did you learn that somewhere already, Ethan, or did you look it up? That's nice. Where did you just Google it? Wikipedia? Yeah, I'd be really interested to. Yeah, that's cool that you found a good resource. Yeah. And I'm sure that the wording was different, but if the logic is there, you're gold. So guys, one other we need to talk about. So hopefully now we're on the big picture idea. Why does adding salt to water make the boiling point go up? Water's attracted to salt. The strong attractions are hard to break. Gotta heat it up hotter to get them to boil. But guys, now we're ready to talk about the other question. Why do we salt roads in the winter here in Utah? And you guys know the answer, right? It makes the ice go away. But guys, the question is why? And that is the second colligative property that you need to understand. This is called the freezing point depression colligative property. And guys, it goes like this. This one's interesting. I think you're gonna like this one. So guys, the question we need to ask is why? Why does adding salt to water make the freezing point go down? And then to finish this, we'll talk about, so then why do we put salt on the roads? So guys, check this out. Here we've got liquid water, right? These balls right here are going to represent salt. I wish that these were gray, but they made them blue. You get the idea. So we're going to dissolve some salt in the water. So now we've got salt water. You good on that? So you can see the ions of salt in the water like so. So guys, this is what salt water looks like at a molecular level. This is what ice looks like at a molecular level. So Why does adding salt to water make the freezing point go down? Well, guys, the idea is this. I'm going to take this out so we can play with it more easily. So, guys, here, imagine it's still in the beaker. So here's our beaker full of water, and here's our ice. What will happen is a couple of these water molecules will get together, and they'll stick, and they'll start to form ice. And that becomes a crystal upon which the rest of the ice chunk is going to grow. And then what will happen is, once we've got a couple frozen molecules of water, other molecules of water will then bump into the crystal and they'll stick. And when they stick, it just makes the ice crystal bigger and bigger and bigger. So literally, guys, when water freezes, what it has to do is it's got to let go of the liquid water in order to stick to the ice crystal. Does that make sense? But here's the trick. What about these water molecules that are stuck to the salt? What do you know about the force of attraction between the water and the salt? It's really strong. And because these forces of attraction are stronger, it's harder to get the water molecules to stick to the ice crystal. And as a result, you've got to cool it down more to get it to freeze. Now understand, guys, that entire idea depends on you understanding this. Did you guys know this? That when you freeze water, when you freeze salt water, the salt is not in the ice. Did you guys know that? When you freeze water, the salt does not go in the water. It doesn't go in the ice. So guys, if you don't believe me, try this at home. Take a glass of water, put a little bit of salt in it and dissolve it. Then taste it so you can taste that it's salt water. Then guys, put it in the freezer and allow it to freeze until you get 3 or 4 millimeters of ice on top of the water. And then do this. Chip the ice out of the cup and grab the ice out of the glass and then rinse it off so there's not any more liquid salt water on the ice, and then eat it. It won't taste salty. Because guys, when you freeze salt water, the salt does not get trapped in the water. So as this salt water freezes, the water has got to break free from the salt ions and stick to the ice crystal. Now remember that this water is tightly attracted to the salt, and because this is tightly attracted, the salt makes it harder for it to freeze, so you've got to cool it down even more to get it to turn into ice. Does that make sense? So guys, this then is how we summarize that idea. And it goes like this. Why does adding salt to water make the freezing point go down? Well, it goes like this. Sounds familiar, right? If the solute dissolves, the intermolecular forces are stronger. How do we know? Because if they weren't, it wouldn't dissolve. Same as the previous logic. But guys, if this is true, therefore, these stronger attractions make it harder for the water molecules to leave the salt and go become ice. As a result, you've got to cool it down even more to get the water to freeze, and the freezing point goes down. So guys, to wrap up the day, let's finally answer the question. Why do we put salt on our roads? Let's let you finish this up, and then we'll talk about that, and then we'll talk about why they don't put salt on the roads in Wyoming, and we'll call it a day. Understand, guys, that you will have homework. Just a minute, Miles. You will have homework as a result of today. It's assignment number 4 in your homework packet for the unit. Guys, understand, these questions are on the test. Some of them almost exactly the way they are in the homework. But guys, understand, we are not going to grade this homework assignment on Friday. I won't be here. We're not going to, and importantly, my computer won't be here, so there's no way for Mrs. Clay to do this with you. And if the sub is the one in charge, I certainly wouldn't ask them to do this. So guys, you will not grade this assignment until Tuesday. But it will be on the test. So, you guys all done here? Okay, so let's talk. And Miles, I know you have a question, but hang on to it. So guys, why then do we put salt on our roads? So let's be honest. You guys think in Fahrenheit and not Celsius, right? Is that okay? So guys, do this. Well, you don't need to do this, but this is the idea. So this is the freezing point of water. 32 degrees Fahrenheit, which is 0 Celsius. So guys, imagine, and they promise this is going to happen, storm on Friday. So you get up Saturday morning, you check the snow report, and oh my gosh, it snowed at Sundance, right? So you're like, I'm going skiing. I probably will too. So guys, you're headed skiing and you're driving up the canyon and your car is new enough that it has a thermometer on the dashboard, and you look at the thermometer on the dashboard as you're driving up Provo Canyon and the thermometer says 25 degrees Fahrenheit. What should be going through your head? Look out for ice. Because guys, we're not talking Celsius. We're talking Fahrenheit. So if it's 25 degrees Fahrenheit, you are 7 degrees below the freezing point of water, and those roads, if they're wet, are going to be covered in ice. So what do we do about that in order to get rid of the ice? Well, guys, what we do is we put salt on the roads. And what does the salt do to the freezing point of water? Makes it go down. So if we add salt to the water that's on our roads, we can actually drop the freezing point down to, say, 20 degrees Fahrenheit. So now we have a new freezing point because we've added salt to the roads. Well, guys, if we can add enough salt to the roads to make the freezing point below the temperature of the air, guess what happens to the ice? It melts. And then overnight, when the temperature drops again, if the temperature doesn't get down to 20, it also won't freeze. Do you see how we get both benefits? So putting salt on the ice causes it to melt, and then it won't refreeze overnight so long as the temperature doesn't get down to the new freezing point that was created by the addition of the salt. So guys, now this, why don't they even waste their time putting salt on the roads in Wyoming? Say it again. Who was that? Yes, but too cold to what? Yeah. Guys, it is so cold in Wyoming that they can't put enough salt on the roads to get the freezing point below the temperature that it is outside. You can't, on a really cold Wyoming day, you can't put enough salt on the roads to get the ice to melt. So what do they do instead? They put sand on the roads, and that provides traction even though the roads are still covered in ice. There you have it. So guys, that is how this all works relative to putting salt on our roads. We now have about 5 or 6 minutes left. I don't know that necessarily you need to be digging into the homework, but guys, we are now doing pride reports. So sit tight. I need to print my pride report. Again, I will not see you Friday, but I will see you guys tonight, right? 7 o'clock for our last home wrestling match. It's senior night, and of course you guys are all going to be there to support our wrestlers, because that's what